Hi there, everyone, and welcome to the Mat 211 review on Maxima and Minima. So for today, we are going to look at this beautiful graph here, and we're going to indicate if the leftmost blue point, that's this guy here, is a critical point. And if it is a critical point, we're going to classify whether it is a relative maximum, a relative minimum, or a saddle point. We're going to repeat this with the middle purple point. That's this guy here. He's kind of purple. And the rightmost green point, which is this guy here. So let's start with our blue point. This guy here. So first things first, we want to determine whether or not this is a critical point. So for critical points, we want to look at the partial derivatives with respect to x and y. And we need the partial derivatives with respect to, so whatever this function is, and we don't know what this function is, with respect to x, we need that to equal 0. And we also need the partial derivative of f with respect to y to equal 0. So when we think about taking the partial derivative, and we'll be kind of eyeballing it here, we're thinking about if we had the partial derivative of x, we're going to hold y constant and look at how x is varying at our point. And we're going to assume that this point is right at the tippy top of this little lump here. So if we think about that, we would be holding y constant. So we'd be following along this line here, if I can draw it kind of straight. Let's try that again. We'd be following kind of along this line, and it'd come around the other side here. So x would be varying, but y is held at a fixed value. It's just 1 point. So if we think about this, if we just look at it as a cross section kind of from this direction, so flattening it out so that our x is increasing here, and we just have some value of y. You don't know quite where we are in y, but we'd have something, our function would look something like this, flattened out at that point, except, nicer. So, and since we're assuming that this point is right at the tippy top, it would be right at the tippy top of this point, or this curve as well, since we're just taking this cross section. So we know that when we have a point that is right at the apex of, a concavity here, we know that that is going to have a derivative equal to 0 at that point. So our x would have a derivative equal to, or our partial, dang it, our partial, there we go, of f with respect to x is equal to 0. And really, this should probably don't even want to draw our y here because that makes it a little confusing. So let's redraw this just to have our x varying along here. So we can do the same thing in the other direction, thinking about our partial with respect to y. So that would be holding x constant and looking at how y is varying. So since this is at the tippy top, it'd be following along some line here. And we can do the same thing. We can take a cross section of it. So let's erase this. And it'd be a little steeper, it looks like, but it'd be kind of like up here again. And this would be as y is varying this time. So this time we're looking at this, we're taking a cross section of y holding x constant. So we're looking at it from this direction. So again, we're going to assume that our point is at the very tippy top here, so right up there. And so this means, because it's at the very tippy top, it means our partial with respect to y is also equal to 0. So this is satisfied for our blue point here. So we know that our blue point is a critical point. Now, the next thing we want to look at is whether this point is a relative maximum, a relative minimum, or a saddle point. So this will only be true, one of these, particular categories will only be the case if it's already a critical point. So we want to look at the concavity of partial x and partial y. What this means is, are we doing this or are we doing this? So around our point, is it decreasing on both sides? Is it increasing on both sides? So we want to think about this in each direction again. So first we're going to think about our partial with respect to x. So we know that that looked something like this. So that's our cross section from this side. And so we see that it is negative in this direction. So around this point, I'll just draw him in there for reference. Around this point, it's decreasing on either side. Similarly, for our y direction, for our partial of f with respect to y, we have, again, something that looks like this with our point nested up here. So again, we know that it is decreasing on both sides. So our concavity is negative for both of these, and that means that it is a relative maximum. Or a local maximum is another way to term that. So let's write that in up here so we can remember. So we can call it a relative max. All right, so that does it for our blue point. Let's move on to our purple point, this guy. So again, I'm not going to draw it again, but we can see that our partial with respect to x, this is at the bottom. So our partial with respect to x is equal to 0. So that part's true. And our partial with respect to y is also equal to 0 because it's decreasing on either side. So that's true. So we do know that this is a critical point. So we've got that first part sorted. Oops. Erase my arrow here. There we go. So we know it's a critical point. All right. Now we want to figure out whether it's a relative maximum, a relative minimum, or a saddle point. So it will be a relative maximum if we have our partial derivatives are going to be decreasing on either side of the point. So that would mean that it's negative concave. And so that would have to be true for both the x and y direction. And it's going to be relative minimum if the partials in both directions are increasing on either side. So you have positive concavity in that case. But if you have a situation where one is doing this in one direction and the other is doing this in the other direction, then this is where you have what's called a saddle point. So we can draw this out just to be clear. So if we think about our partial with respect to x, that's going to be along this line here. We have something that's doing this with our point here in the bottom. So we have positive concavity. or it's, you know, increasing on either side of our point. So similarly, if we look at this direction for our partial with respect to y, we notice in this case, we have something like that looks like that with our point here in the center. So since we have one direction, we have positive concavity, the other direction we have negative concavity, we know that this is going to be, this purple point here is going to be a saddle point. And it kind of looks like a little saddle if you look like it. You know, looks like you can kind of sit in it and ride a horse or something. So let's write that in here. This is a saddle point. Ba-ba. All right. Last but not least, let's look at our green point here. Get rid of all our check marks because this is not necessarily true. All right. So this point, we'll look at our partial. Let's look at our partial with respect to y first. So that's running somewhere like along here. So since this is not doing this or doing this, where our point is in the center, we know right away that our partial derivative with respect to y is not equal to 0. So let me write that in. Partial derivative, our partial derivative with respect to y does not equal 0, because instead we're doing something like this with our point here. So our point's actively changing at this particular spot. And in fact, if we look at the direction this is going, so x is increasing in this direction, and oh, so this is actually the partial with respect to x, my bad. X, there we go. So we know that as x is changing here, we can see that this is sloping downwards. So, give me my eraser here. There you go. We don't even really need to check our partial with respect to y, because we can kind of eyeball it and see that it's also changing at this point. But the fact that our partial with respect to x is not equal to 0 is enough for us to say that this is not a critical point. So therefore, we don't even have to check whether it's relative max, relative min, or saddle point, because it's not going to be any of those things, because it's not a critical point. So that's it. We've classified our 3 points. We can usually tell kind of from inspection if we know that the point is sitting on top of the hump here, or right in the middle of the saddle, or if we had something where it was like dipping in both directions, you know, that would be a local min. And then if we have points here that are just kind of floating randomly on the surface in some, you know, non-max or min spot, then we know that those are not going to be a critical point. So that's it. And before I go, I just wanted to remind everybody that if you are looking for any additional tutoring or academic support at ASU, you can visit our tutoring center website, tutoring.asu.edu, and you can find all of our tutoring services there. You can also go directly to the tutor search function at this full link here, and that'll allow you to find tutoring services for a specific course. So thanks so much, and have a great rest of your day.